You know, you probably used a dozen computers before you even had your morning coffee. And no, I'm not talking about your phone or your laptop. I'm talking about the tiny, hidden brains that are secretly running our world. Today, we're going to pull back that curtain.
So what do they have in common? Well, on the surface, not a whole lot, right? They all seem like pretty simple single-purpose gadgets. But inside each and every one of them is a tiny, dedicated brain, a specialized computer making all the decisions.
And just to be clear, we are not talking about a miniature version of the computer on your desk. This is a totally different kind of machine. It's one of the great unsung heroes of the modern world, and it's called a microcontroller.
So what's the big deal? Well, the magic of a microcontroller is that it's a complete, self-contained system on a single piece of silicon. I mean, everything it needs, the brain, the memory, the connections to the outside world, it's all baked right in from the start.
All right, so to really get our heads around this, let's compare it to something we all know really well, the computer sitting on your desk.
I love this analogy because it just clicks. Think of a microcontroller like a tiny, super efficient little office, you know? It has one specialist who does one job and does it perfectly. A PC, on the other hand, that's the massive corporate headquarters. It's powerful, sure, and it can do thousands of different things, but man, is it expensive and power-hungry.
And it's this tiny office philosophy, this intense focus on doing one single job perfectly, that leads to some just brilliant design choices. It's what makes them so incredibly good at what they do.
A huge part of that efficiency comes down to how they manage information traffic. You see, your PC uses something called a von Neumann architecture. Just picture a single-lane highway for everything, both the instructions for what to do and the actual data. It works, but you can imagine the traffic jams, right? Microcontrollers, though, they use a Harvard architecture. Now, this is like having two separate, dedicated superhighways. One is just for instructions, and the other is just for data. This means the CPU can grab its next instruction while it's working on data at the exact same time. No bottlenecks, no traffic jams, just pure speed.
This whole specialist vibe even extends to the language they speak. PCs use what we call a complex instruction set, or CISC. One single command can kick off a whole bunch of different operations. But microcontrollers? Nope. They prefer a reduced instruction set, or RISC. And that means the CPU is working with a small vocabulary of really simple, really fast instructions. It's like having that specialist worker again. They do one simple task, but they do it incredibly fast. And the beautiful thing is, this makes the hardware itself smaller, way cheaper, and so much more power efficient.
Okay, so let's pop the hood on our tiny office and see what components make this whole system-on-a-chip thing work.
Right at the heart of everything is the CPU, the central processing unit. This is our tireless little worker, and it's caught in this endless, super fast cycle. Fetch an instruction, decode it to figure out what it means, and then execute it. Fetch, decode, execute. Over and over, millions of times every single second. It's relentless. But wait, where is it getting these instructions from? Well, that's where flash memory comes in. This is the permanent filing cabinet for our tiny office. It's where the program code, the big instruction manual, is stored. And the key thing here is, it holds onto that information even when you unplug the device.
Okay, so for its day-to-day work, the stuff it's actively thinking about, the CPU uses SRAM. This is the worker's desk. It's super fast, easy to grab things from, but it's a temporary workspace. As soon as the power goes out, poof, the desk is wiped completely clean.
So you can see this creates a really interesting trade-off. The desk, the SRAM, is lightning fast and can be written to over and over again without wearing out, but it's super expensive and you don't get much of it. The filing cabinet, the flash memory, is cheap and you can fit a ton of stuff in there, but it's slower to write to and it actually wears out over time. It's this constant balancing act between speed, space, and cost.
So just how small are we talking for that SRAM desk space? Let's take a classic example. The microcontroller in the Arduino Uno, a favorite for hobbyists. It has just 2 kilobytes of SRAM. That's it, 2 kilobytes. That's the entire desk our little worker has to juggle every single active task.
All right, so we've got our worker, our desk, and our filing cabinet. But how does this tiny office actually boot up in the morning? What really happens the moment you flip that switch?
It's this really precise morning ritual. First, the power comes on and gets stable. Think of it like the lights flickering on. Then our worker, the CPU, wakes up and immediately goes to a specific spot in the filing cabinet to grab its very first instruction for the day. It uses that to get the office clock ticking correctly and then, and this is the crucial part, it prepares its desk.
It copies all the essential notes it needs for the day from that permanent filing cabinet over to its temporary desk, the SRAM. It's only after that desk is perfectly set up that the main work can finally begin.
Now, this whole design, being super optimized and working with very limited resources, is exactly what makes microcontrollers so powerful and so cheap. But living on the edge like that creates some really unique and kind of fascinating challenges for the developers who have to program these things.
I mean, just think about it for a second. With only a couple kilobytes of disk space, what do you think happens when the program our little worker is running tries to use more temporary notes and scratch paper than can actually fit on the desk?
Well, what happens is a catastrophic failure. It's called a stack overflow. Basically, the part of the desk reserved for temporary notes, we call that the stack, it just keeps growing and growing until it spills over and starts writing all over other important data on the desk. You've got notes from one task literally corrupting the work of another.
And the fallout from this is, well, it's absolute chaos. The whole system might just crash. Or, even weirder, variables might start changing their values seemingly at random. The program can start jumping to weird places and doing things it was never supposed to do. It's a total nightmare to figure out because the very evidence of what went wrong has been scribbled over and destroyed.
And this brings us to what might be the most important point of all. In the world of microcontrollers, bugs aren't just these abstract lines of code gone wrong. No, they are the direct physical consequences of the hardware's limitations. Running out of memory isn't just a polite error message on your screen. It's a hard physical limit that can bring the entire device to its knees.
So, as we continue to weave computation deeper and deeper into the fabric of our lives, into everything from our toasters to our cars, it's pretty clear that these tiny, ultra-efficient offices on a chip are the invisible engines powering our future. And that leaves us with a really interesting question to ponder. Is that future going to be built by the giant, all-powerful corporate HQ, or by billions upon billions of these tiny, dedicated, and specialized little offices?